Hello, everybody. So here we're doing problem 6.10, and we're talking about a water molecule in different kind of states. So we're given that the frequency is equals to 4.8 times 10 to the power of 13 hertz, and the excited energy levels therefore are S1 is equals to 1 half HF. Oops, right. F, yeah. E of S2 is equals to 1 half of H, oh sorry, 3 half of HF, ES3 then equals to 5 half HF, and then we can go ahead and do the rest. However, uh, to solve it, we don't need to calculate every single one of those. Oops. Okay. And we can say, for example, well, not for example, to calculate the probability, then we need to find the uh, partition function. The partition function is then equals to, again, we said the sum of the states, so negative E of S, depending on S, of course, by KT, which ends up being E at the power of negative 1 half HF times 1 over KT. Okay. We have a temperature. Okay, 300 Kelvin. I forgot to mention that. So temperature is equal to 300 Kelvin, because we actually do need that, plus E to the power of negative 3 over 2 HF times 1 over KT, plus E to the power of negative 5 over 2 HF times 1 over KT, plus so on. So I'm just going to use the first three, to be honest. I think it's going to be enough. Just start calculating them. So we have 1 half HF. So we have uh, E at the power of negative 1 over 2 times H, which is our Planck's constant, which is equals to 4.136 times 10 to the power of negative 15 electron volts per second, times the frequency, which we're told is 4.8 times 10 to the power of 13, divided by KT. So K is 8.6 times 10 to the power of negative 5 times 300. So the first one ends up being, actually, I'm right over here, okay, 0.0213 plus the second one is 9.71 times 10 to the power of negative 6 plus the last one, which is 5 half. As you can see, we're already decreasing. We're already at a factor of negative 6, starting from a factor of negative 2. So uh, uh, the main factor is this first one. If we went ahead, did 7 half of HF, for example, this one here, we will get something that really doesn't affect us. So I'm just going to say 4.42 times 10 to the power of negative 9. So all of these together are just going to equals 0.0213. It's exactly what we had before. If we want, we can, I'm just going to say another one, 4, just so it looks a little better. So probability of it being in S1 is then going to be equals to 1 over Z times E to the power of what we just found. So negative E of S1 divided by KT. So we know the values for both. We know this is equals to 0.0213 divided by 0.0213. I had our 4 just so it's a little bit better, but there's really not much to it. In fact, it's equals to 0.9995. Probability of it being in S2 is equals to 1 over Z. Again, I can just write the number direct, so 9.71 1 times 10 to the power of negative 6 divided by 0.02134. So let's plug in the calculator, which is equals to about 0. Actually, I'm going to write it. Scientific form 4.55 times 10 to the power of negative 4. Probability of it being an S3 is equals to 4.42 times 10 to the power of negative 9 divided by 0.02134, which ends up being, divided by this. 2.1 times 10 to the power of negative 7. Okay, so these are our functions. These are probability, to be in the first two excited states and in the ground state. So it's pretty much going to be in the ground state all the time with 0.0995. We have to do the same calculations, this time having a temperature of 700 Kelvin. So double we have until now. So let's recalculate our partition function. So e to the power of negative HF. We have to recalculate the whole thing. So it would be H 1/2 HF divided by 1 over KT, times 1 over KT, of course, plus blah, blah, blah. So you already know what comes after. I'm not going to even spend time rewriting it. And we get 0.99226 for the first one. And then for the second one, we obtain 0.007107 plus, I'm just trying to add a little bit of significant figures, so it's a little bit better for our calculations, plus 2.63 times 10 to the power negative 4. Now, what we expect is to have a higher probability because we have a higher temperature. So probability of S1 is equals to, of course, this one will lower a little bit. So we have the sum of all these. Actually, I forgot to do that. Is equals to 0.19963. So the first one will then be 0.9631. This comes from the 0.19226 divided by 0.19963. The second one would be equals to 0. I'm going to write it just to make sure that you understand it. Divided by 0.19963. So this is equals to 0.03560. And then probability of S3 on this second excited stage is 0. Actually, I'm going to write it just so you remember. 0. We said 263 times 10 to the power negative 4 divided by 0.19963 is equals to about 0.00132. As you can see, we do have higher values for our excited stages. This is because we, in fact, do have a higher temperature, except for the first ground state, which of course decreases in probability. I hope this is helpful. Let me know if you have any questions, and I'll see you next time.